Okay, so our project about fluorescence of dental materials aim to characterize the fluorescence of teeth and dental resin. So the fluorescence we study in our project consists by the absorption of blue light or UV light by teeth or the dental resin, and the emission of visible light. Fluorescence is what give to the teeth this pure whiteness. So why we need to study this? Because for dental surgery, obviously it's very important that the dental material reproduce exactly the good color and the good brightness adapted to each person. But we cannot forget this fluorescent behavior in order to have to no don't notice the difference in case of an exposition to UV or blue light. So for our laboratory experiment, we use a laser at a wavelength of 405 nanometer in the UV domain. We use also a filter to suppress this wavelength after the sample in order to record only the fluorescent spectrum in the spectrophotometer. So on the right, you can see our series of samples that we use from different thicknesses. From 0.3 millimeters up to 1.8 millimeter. But in order to have access to higher thicknesses, we use a technique of matching of indices in order to suppress the interfaces when we superpose two samples. So in this picture, you can see the configuration of our experimental bench in the transmission with a laser, the support for the sample. You can see the filter and the lens that focuses the transmitted light into the optical fiber into the spectrophotometer. And here are the results of our fluorescent spectrum in transmission. You can see that the shape of the spectrum is conserved with the thicknesses, but there is an evolution of the amplitude. So on the right, we measure the evolution of the maximum in function of the thickness, and you will see that it depends according to the extended Kubelka model. So now Yacine will explain you in the configuration in reflection.
Yes. So for the reflection, we put the laser in an almost normal configuration. We have approximately 10 degrees between the optical axis and the laser. Next slide, please. We measure the spectrum in reflection. As for the transmission, we have the same shape for all thicknesses. For the 0.3 millimeter, we have a low level because the sample is translucent. Next slide, please. After measuring the transmission and the reflection spectra, we plot the maximum as a function of thickness. For transmission, first regime where we notice that the maximum of fluorescence increases according to the thickness. Then a second regime where the level will drop because of the UV light be absorbed, emitted, and attenuated in the sample. For the reflection, we have a first regime identical to the transmission until reaching a regime where the maximum in reflections becomes constant. We solve the system of equation with the term related to the fluorescence, and we notice a consistent with the Kubelka-Munck model. Next slide, please. The phenomenon of quenching corresponds to the fact the incident ray is totally attenuated by the sample without using a filter. There is a thickness limit where this phenomenon is reached. Next slide, please. We can see for a thickness of 2.4 millimeter, the incident ray still has a great impact. His impact will decrease with the increase of the thickness until it disappears. Next slide, please. We can see the quenching limit between 3.6 and 3.9 millimeter. Next slide. And to conclude, the appearance of dental materials under UV light is essential. Laboratory experiment is consistent with extended Kubelka-Munck model. And for the reflection, when the thickness increases, they imitate light also. And for the transmission, when the thickness increases, the emitted light decreases. Thank you for your attention. And thank you to Vincent Duveillet and Mathieu Hébert.